Hi everyone, our next review is going to deal with solids, and as we think of kinetic molecular theory and think of the idea that to get from a solid to a liquid to a gas, we need to add heat. Solids are obviously on the lowest end of that spectrum, which means that they have the least amount of heat associated with them, and that gives rise to some various properties. So they don't really slide past one another in terms of their atoms, but the atoms or the particles are set in fixed positions. But it does allow them to have really strong forces, right? So the forces between molecules or between atoms or between ions in a solid are really typically very strong. And we're going to talk about two broad categories, amorphous and crystalline. So let's talk about amorphous. Amorphous solids don't have a very definite shape. They're kind of these more random arrangements. Here's a pretty good example of an amorphous solid. You'll see that there's some structure there, but it's not very uniform like some of the ones we'll see in a second. And it turns out that sometimes these are called supercooled liquids because they actually exhibit properties of both liquids and solids from time to time. So we have this tendency in chemistry to think of things as either black or white, this or that, but there are a lot of places where things don't really follow the categories that we define for them, and this is one of those places where it kind of fits in between. And so what's really cool is if you look at really old, like centuries old glass, if you look at a window, oftentimes the bottom of the window is thicker than the top because over time it's kind of drooped down a little bit towards the bottom. Not enough to break or anything like that, but the supercooled liquid or this amorphous solid has changed its structure just a bit. Let's talk about crystalline solids. So these are a bit more highly arranged. They typically have a repeating pattern. There are some definitions to know. So a unit cell is basically the smallest part of one of these solids that maintains the chemical and physical property of that structure. Hydrates are if we take something like this crystal here and we sneak a water molecule in between the atoms or ions existing in that crystal. And there are four main types of these crystalline solids that we should talk about. So number one is metallic solid. These are metals, right? And remember, in a metal, the electrons are not belonging to any one atom or any one nucleus. They're free to move around. So that means, imagine that right here, you have this piece of metal attached into, I don't know, an outlet, like so. And over here, you touch it, right? So here is your hand. I know I'm an artist. Then you can get shocked, right? Because the electrons are able to transfer that charge from over here to your hand, and it's bad news for everyone involved, right? But it does give rise to some cool properties, allowing metals to conduct. It also means that metals are rather malleable, meaning they can be pounded into thin sheets, or you can draw them into wires, which is called ductility. Our next type is a molecular solid. Remember, molecular comes from molecule. Molecule is the term that we give to covalently bonded compounds. So if you have a covalently bonded molecule, it's going to come together to make a molecular solid. Because these are only held together by intermolecular forces like dipole-dipole hydrogen bond or LDF, they have relatively low melting points, meaning we can kind of break them down rather easily. And they don't have free ions, so they can't conduct heat, they can't conduct electricity, because they can't move that charge from one place to another. But indeed, it is easy to break them apart, and one of the ways we measure the ability to break something apart is the melting point. So just briefly, if you think about something like water, water in its solid form is called ice, and it has a formula, H2O. Water in its liquid form we just call water, and it's H2O. And water in its gaseous form we call steam, and it's still H2O. So there's a misconception whenever you melt something or you turn it to a gas that you're actually breaking a bond. But remember, you're not breaking this bond between hydrogen and oxygen. Whether it's a solid, a liquid, or a gas, you still have H2O. What you're breaking is the force between the partially positive oxygen and the partially positive hydrogen. So that red line is what you're breaking apart. And because these molecules often don't have very strong intermolecular forces holding them together, it's relatively easy to break those, and so they have low melting points. It's easier for us to separate one molecule from another. Compare and contrast that with ionic solids. Ionic solids have a full-blown electron transfer going on. So if I wanted to split these positives from these negatives, that's going to take a lot of work. That's going to take a really high melting point. We're going to need a lot of energy to do that. It also turns out that ionic solids tend to be rather brittle because if you're able to break this, then the whole sheet is going to just kind of disintegrate over to the side. So think of table salt, right? Table salt is pretty brittle. If you have granular table salt and you squeeze it between your fingers, you're going to notice that it crumbles pretty easily because it's crumbling along these very defined sheets that run through this crystal structure. Our last type that we'll define is called a covalent network solid. So a covalent network solid is actually made up of atoms as opposed to molecules. So imagine a whole bunch of carbon atoms. We have 3 different examples here that are just combinations of carbon atoms. So we'll see more of these in class. But these covalent network solids have covalent bonds holding them together, but instead of molecules, we're holding together individual atoms. And carbon does this really well because it has 4 bonding locations. So again, we'll take a look at this a little bit more in depth whenever we're in class.